And the second point I'm going to calculate is the pH at equivalence. Okay, so we're going to go back, and the first thing that we need to do to work out the pH at equivalence is to make sure we've got the the titration equation. So in this case, the titration equation looks like this. Righty-ho, and so our key idea is that at equivalence point, we have added equal moles of the acid and the base, and so therefore at equivalence point in our beaker we essentially just have the products. So when looking at these products, we can eliminate Cl- because it doesn't accept or donate protons, but this ion here does. So if I write an equation for this ion here reacting with water, we know that at this point it's always going to be a weak reaction, so we're going to use an equilibrium arrow. And you can see that CH3NH3 plus has got an extra proton, so it is going to donate a proton. So at this stage we know we are calculating the pH of a weak acid at equivalence point. So this is our key equation, and we're going to write a Ka expression for that. So that's just products over reactants. So our Ka expression is always for the weak acid that reacts with water to produce H3O+. I always see students writing Ka expressions for random equations. No, they're only for this one type of equation here. Right, so now we need to substitute in our values and rearrange and solve for the H3O+, because that's going to be how we figure out the pH. So we got given the pKa in the original question, and the pKa was 10.7. So to find out the Ka, we just have to do 10 to the power of the negative pKa. To do that on my calculator, I go shift log, so that's inverse log negative 10.7. Oops, shift log negative 10.7. I'm having trouble with my calculator. Let's try it one more time. Negative 10.7. Thank you. And that gives me 1.995 times 10 to the power of negative 11. So that's the number that goes in here. We're going to make the same assumption that we've only got one substance contributing to the pH, so these two are equal and we're going to call them X. This bit here's the tricky one. We were told that we had 0.0255 moles per litre of both the original acid and base, so the CH3NH2 and the HCl. This is a simple question, therefore, in that if we have equal concentrations, then at equivalence point we have added 15 mils of each. Equal concentrations, equal volumes. Therefore, we have doubled the effective volume. Therefore, we must half this concentration. So if we double the volume, we half the concentration. Right, so now we've got everything we need. We substitute this value in, equals x squared over 0.0255 divided by 2, which is 0.01275. So our x, which in this case is our H3O plus, 0.01275 multiplied by 1.995 times 10 to the power of negative 11. And then I'm going to square root that answer to give me 5.043 times 10 to the minus 7, and that's the H3O plus. And then if I negative log that, I get 6.30. And that is my pH at equivalence. Just check it for meaning. Is it the approximate pH of a weak acid? Yep, that's not too bad at all. So that's our second point, 6.30.